Okay, hi. Assalamualaikum. So we continue. We have seen that in the previous lecture, we have seen that you have damped force vibration. Basically, these are the main equations that we looked at in terms of what we call this as the amplitude ratio equation, and also phi is the angle. So how do we actually, if we actually plot this, how does it look like? So this is how it looks like. Basically, you have your amplitude ratio as the y-axis, your frequency ratio as the x-axis. So you can see that basically at a value of 1 here, where your r equals to 1. So we already defined r equals to omega over omega n, which is also called as frequency ratio. So you notice that these are all dimensionless. So that's why it's always true for any single degree of freedom system with input, yeah, or force vibration. So when you see at 1, so you can see what happened. So what happened is basically as your zeta, you can see these numbers here. These are all the zeta. So each of the line here representing at different zeta. Yeah. So basically, if you look at go straight to this line here, 1 at r equals to 1, you can actually see that this line here, you can actually see that there is kind of like a very near to that line, there's kind of like a peak, but it actually slanted a little bit, skewed a little bit to the left hand side of this line. So what it says basically, as you increase the decrease the damping, you can see that this is smaller than 3, right? So as you have increase the damping, okay, what happens to the peak basically, class? So the peak goes down. So basically amplitude ratio x over static deflection goes down as at r equals to 1. So we are looking at r equals to 1, and you can see at a very very small zeta. Okay, so at very small zeta, okay, it will go to infinity. Your x over static deflection goes to infinity. Okay, especially at 0, you wouldn't expect that. Yeah. Why? Because you can also refer to this equation. Okay, so when you actually have value of omega n equals to 1, then this will obviously goes to 0. So this one divided by 2 zeta. So if zeta is very, very small, you dividing it into very small number. So this will actually goes very, very high number, large number, if zeta is small. So that makes sense if you actually look at the equation. So very small number of zeta, so we are talking at r equals to 1, yeah, somewhere there. Then you would have kind of like resonance from phenomena. If you have just like it's actually merging to undamped condition, like merging to undamped condition when you have very very small damping. So this one is the phase angle. You have the angle and also the frequency ratio. You can see that it actually pivoted at r equals to 1. Alright, so you can also take a look at the equations. So basically tangent inverse of infinity there. So it's actually at this angle. At this angle there is pivoted at 90 degree. Okay. So in summary, okay, we can actually write the differential equation and its complete solution, including the transient term. So remember, complete solution consists of the free vibration part, or your XH. So this is free vibration. Okay, and this part is what we call the steady state, which is also particular solution. Okay, how do they get this? This is actually your capital X based on the equation that I've showed previously, which is basically from this equation or this equation. So this part is your capital X. So we just substitute basically. Okay, so this is capital X cosine omega t minus phi. So what we're doing here is we just substituting based on this solution. Okay, remember? So this is the solution. So you know what X is. So you just substitute, which is this formula. So that's how you get this particular solution, capital X, or the amplitude. How do we get this equation? So maybe you can refer to your list of equation downloaded from Moodle. Take a look at list of equation. You take a look at where you have an underdamped condition. Underdamped condition. So you will find that there is an equation that relates how do you write the solution for the free vibration for underdamped condition. I think we also have derived this in chapter 2. So basically this part is chapter 2 basically. Yeah. So please refer that in your notes. So maybe on the vector I will skip a little bit. I would like to focus on the quality factor. Okay, the quality factor and bandwidth. So when the damping ratio is increased, the two phenomena is observed in the vicinity of the resonance frequency. Amplitude tends to decrease. So I think I have explained this. And the amplitude tends to shift to the left. So I said just now it's skewed based on the graph. So you can actually find the frequency that relates to this. So if you take a look at how do you determine what kind of frequency that you experience, is basically this is the maximum value of the frequency. Okay, and then this is the maximum value of the amplitude ratio under when actually based on the peak where you have that omega over omega n equals to 1. So how do you determine basically what we call the quality factor is basically from this equation of the peak value of your amplitude ratio, which is 1 over 2 zeta. So in other words, the Q factor is a measure of damping in a system. Alright, so that is how you relate what is quality factor and what is when you have a damping, you can actually determine the damping. So from this value, you can, if you have your quality factor, you can actually calculate your zeta. So what about the definition of bandwidth? Okay, definition of bandwidth is basically if you actually have around your R value is around 1, okay, and then you take the peak value here, which we know from the previous equation is 1 over 2 zeta, and then you go down at a point of Q over, so that is the point, which is Q over square root of 2. Then you can find there are two frequencies that define this. So the two frequencies are what we call the half point points, which are the lower frequency, okay, and the upper frequency. Okay, this lower and upper frequency, or what here we have R1 and R2, are actually define the bandwidth of the frequency. So what we call half power points and bandwidth. So that's the definition. Because sometimes when you actually have vibrations response or maybe electrical signals also, sometimes people say, okay, what's the bandwidth of the signal, or what's the bandwidth of the vibration amplitude. Okay, so this is how we define bandwidth. You go down where the value of the peak is divided with set2, and then find the corresponding frequency. So the difference or range is what we call the bandwidth. So there are also simple equations that you can define when you have a condition of, in this case, for example, you have your zeta is less than 0.5, okay? Then you can actually determine your quality factor in the form of omega n, okay, divided by omega 2 minus omega 1. So these are the frequencies at point R1 and R2. So we have defined that. So let us take a look at this example. We have example 1 here. So we will, in this example, you are asked to find the total response of a single degree of freedom system. So let's say if you want to draw it, you have this M of 10 kilogram, and then you have your C of 20 and your K of 4 kilonewton per meter. Okay, and they gave to you x naught. Okay, means you have initial value that you can use to determine the amplitude, and release from rest at time equals to 0. What it means by that is your V naught. So release from rest means it starts at 0 at t equals 0. Okay, under the following conditions. So you have to determine one, the free vibration. So you have this system, one is free, one is you have force. So basically free vibration is the equation from chapter 2, and the force vibration is from chapter 3, which is this lecture, with this F naught and omega. So basically you have to find two responses. Basically you need to find xh and x steady state, or xp. So let us take a look how we solve this. From this equation, you know that main equation, or the response from chapter 2 is actually, if you have damping system, you would need to calculate the damping and determine whether it's under damped, over damped, or critically damped, because you want to choose which equation you need to use in the list of equation. So in this case, first we calculate the undamped natural frequency, then we get the critical frequency, critical damping, then you can calculate your damping ratio. So since your zeta is less than 1, then you know you have to use the underdamped equation. Alright, so after that, you can see that once you get your underdamped equation, you can actually go to your list of equations. How do you get this? See the list of equation that you should download. From Moodle. Okay, so and take a look at under free vibration. Okay, and then you go to under damped, because zeta is less than 1. So you will find that you have this equation. Yeah. So before we actually can write this equation, you have to calculate first. So you have to calculate the damped natural frequency omega d, because you want to substitute into the formula. You already have omega n, you have zeta, and you want to know what is x naught. Then you calculate the ratio of oscillating frequency because you already have omega and omega n. Then you can just substitute all the values. Okay, for x naught, in the list of equation, you can take a look at A. I think the amplitude was defined as A in the list of equation. So then you can calculate. So all these these two equations are all in the list of equation. It's just a matter of substituting. Then you get your free response. Okay. So from there, you can also calculate your force response. So remember, in this problem, your F naught is 100. So they give you all the values there. So in this case, they give you specifically that is a cosine function. So if you have a cosine function, then you automatically know that your XSS is capital X cosine, okay, omega t. Okay, is that all? No, right? Because you have damping, so you have to minus phi. So don't forget. So this is the steady state solution. So that's why here your capital X, so basically F naught divided by K blah blah blah, this term is basically your X naught. Yeah, the X naught equation. And then you have to write your cosine, which is this solution, cosine omega t minus phi. So you have to substitute into this equation in terms of phi. Okay, so this is how they calculate. They calculate the phi and your F naught divided by K. So this term here is basically your X, capital X. So you can calculate and substitute the values. So finally, your steady state solution is in terms of a capital X naught, or capital X, we call it cosine omega t. So this is omega. You already calculate that, minus phi. So this is the phi value. Yeah, this is omega t minus phi. Alright. So I hope you can understand the solution. After that, you just add them up, because total response is XH, which is the free vibration equation from chapter 2, and XP is the equation that we have just learned in this class. So I guess that's all for the solutions. So thank you very much. I'll see you in the next class.